Here we are. Once again, it's the physics video lecture. Physics 203 video lecture 6. And we're in the middle of Lagrangian mechanics. So let's recapitulate and then move forward. So in the Lagrangian mechanics, we've already done a few things. We've discovered that mechanics can be derived from a variational principle. So we have this that gives us the equations of motion, and we constructed some systems. L equals L of generalized coordinates, generalized velocities, and time. And in fact, we had that kind of standard prototypical Lagrangian now. But I'll just leave this right here, so that's what we have. We have the equations of motion. And then we have symmetries and conservation laws. Well, how about I write this? Plus examples. So we actually constructed some Lagrangians. The next thing was symmetries and conservation laws, which was a generalization of the fact that we find conserved quantities when we have cyclic coordinates. Okay? So symmetries and conservation laws. And yeah, we had cyclic coordinates. So we definitely see that the choice of coordinate systems, try to drive that point home, the choice of coordinate systems is so important. And if you choose the right coordinate system, there will be some cyclic coordinates there, and you have some conserved quantities, and you're on your way. That's the idea. So we're going to continue on in this theme a bit, and we could say the overarching idea here is to find out what can we discover about a mechanical system without actually solving the equations of motion. So, for example, here we discovered that we can get conservation of energy, linear momentum, angular momentum, without actually solving the system. So there's another aspect here, and this is going to be a similar theme, gauge transformations. And this is addressing the different forms that the Lagrangian can take and still describe the same physics. So what we're going to prove is the following. Suppose we have a Lagrangian, I'm going to call it L prime, that differs from the original Lagrangian by some terms that can be expressed as the complete time derivative of the coordinates and of a complete time derivative of an arbitrary function of the coordinates and the time. So L, we're saying, is just of that type here, shorthand Q dot, and T. And since it's a Lagrangian, we have the Euler-Lagrange equations that follow from this principle right here. Okay, so suppose one Lagrangian differs from another by a complete time derivative of an arbitrary function of the coordinates and the time. Well, we can quickly show that this transformation here, which is what this is, transformation from one Lagrangian to another, leaves the equations of motion unchanged. equations of motion are unchanged, and that means the physics is unchanged, and they're both describing the same physics. Are unchanged. And there's a nice example that we'll deal with and maybe make it a homework problem. So, and there's a couple of ways to prove this. You can actually crank out all the derivatives with some pretty major chain rule here, and then you'll find that the Euler-Lagrange, call it operator, on L prime and L leaves the same thing, because if you apply it to this type of expression, all of your terms will cancel identically, or they'll all add up to 0. But that's a lot more work than this simple proof here. So the proof that I want to talk about just depends on the fact that we have a variational principle. So we've got a variational principle. So we have variation of the action equals 0, giving us the equations of motion. So that's what we've been studying, and this S here is, of course, that thing there. So L prime dt from T1 to T2, that's called the action. So this thing, we could say, is the variation of this half of the definition. So L plus dt. And important that the variation was from these fixed endpoints, right? That was part of our construction. So what we have is this. The integral of these fixed endpoints of a complete time derivative is going to give us f of q of t1 and t1 minus f of q of t2, like that. So don't need square bracket. And yeah, we'll put a little bracket around it. Because since, complete time derivative evaluated these fixed endpoints, these are both constants. And let's distribute this. Okay. So we distributed that operation. Now the variation of constants is simply 0. So because we have a variational principle, we don't have to do any fancy calculation at all. This is 0, so variation of a constant equals 0. And what we're left with is that this variational principle is equal to that second one there. So we're going to get the same equation of motion out without actually having had to do all that work. So that already shows you the power of being able to generate your physics from a variational principle. And let's look at the example that I'll put as a homework problem. So the example, and I'll get started. I'll start it for you. So this is a nice basic homework problem. So what we're going to do is consider the Lagrangian of a non-relativistic point mass particle, charged particle in an electromagnetic field. So Lagrangian of a charged particle in an electromagnetic field. In fact, we can do more than just this thing right here, so you gotta be careful not to get carried away. So let's look at what that Lagrangian looks like. We have L equals 1/2 m. I'm just gonna write v squared, okay? And then we have minus q phi, and then we have plus q over c a dot v. Okay. So this is the scalar potential, this is the vector potential. Make sure I'm using the right formalism here. Yes, q over c. It can be done either way. C is the speed of light, so let's go ahead and go with this one right here. So that's the Lagrangian. And let me put a couple notes here before we go on. What we want to do is the gauge transformation for this thing, which is actually quickly done, but make sure we define everything. So here, V is equal to R dot is equal to dr dt, of course, and V squared is just the dot product with itself, right? V squared is equal to V dotted into V. What we have here, phi is equal to phi of R. We could actually have it as a function of R and T in this process. Let's just leave it as a function of R. That'll work well enough. Phi is equal to phi of R, where E is equal to minus gradient of phi. So that's the potential whose derivative gives us the electric field. Okay. Electric field. And A is equal to A of R. Again, we could also make it a function of R and T, but we'll just say A of R. And that is the vector potential. The curl of A is equal to the magnetic field. Okay. So that's what we're talking about here, and that's the Lagrangian. Well, actually, should you take my word for that? One thing we can do is apply the Euler-Lagrange equations to this Lagrangian and make sure we get out the motion of a charged particle, the equation of motion of a charged particle. And possibly we'll do that. But right now I want to talk about the gauge transformation. And what we'll do is this. Let phi prime equal phi minus 1 over c c dt or t, and let a prime equal a plus gradient of c of r and t. So this is our transformation. So phi prime is phi, as defined above here, minus 1 over c times this time derivative, partial derivative. And a prime is a plus the gradient of this self-same function right here. Show that the Lagrangian that you get by plugging these transformed quantities in. Okay. So you're replacing phi by phi prime, and you're replacing a by a prime. Show that that is the complete time derivative of, oh, maybe I should put R here instead of T. Same idea. Okay. Show that the transformed Lagrangian is the original one plus the complete time derivative of some function, okay, which is actually up on the board already. And what you then know is that this transformation of potential, scalar and vector potentials leaves the equations of motion unchanged. So this is something you possibly ran into in electricity and magnetism already in explicit form, and because there are different gauges when you start talking about wave equations, for example. Okay, so there's actually more we can do with this. There's our homework problem. Furthermore, we can use this Lagrangian, and let's go ahead and do this. Let's add this to the homework problem. So this would be part 1 of our homework problem. And part 2 would be show that Euler-Lagrange equations for star, which is this thing right here, lead to m(r) second derivative is equal to qe plus qv cross b. That's what you recognize from electricity and magnetism. Mass times acceleration, that's your electric force, and that's your Lorentz force from the magnetic field. So you want to show that this Lagrangian, given those equations of motion, leads to this equation here. So that's a pretty important one. We're going to use this thing again when we're doing Hamiltonian mechanics, so we're just going to add that to our list of important results. Now, I think this is pretty complete, QE, QV cross B. This could get a little hairy, but what you do is if you can show it for the X component, then you can declare victory, because these, you know, the equations, we can generate them cyclically. And so if you get one, you got all three of them. Okay. Now, what we're looking at is d dt dl. And by the way, do this for, you don't have to do it for L prime here, you just do it for this original L. dl dx dot minus dl dx is equal to 0. You can say R is equal to X, Y, and Z. And just so you see what's going on here, this one will be easy, okay? The gradient of this thing immediately gives you E, so there's no problem there, right? Look at E sub X. Now in terms of A dot V, let's note A dot V is equal to A sub X of X, Y, and Z times this V here, X dot plus A sub Y of X, Y, and Z, Y dot A sub Z of X, Y, and Z, Z dot, okay? So this is a scalar product. I've expanded it out. You're going to take a derivative with respect to X dot, you see what you're going to get. You're going to get the a sub x term here. If you take its time derivative, complete time derivative, you're going to generate a bunch of terms here. Okay, dax dx partial, right, x dot, and so forth. So with d, I'll write that out so you see where we're at. D over dt d a let's go ahead. D over dt like this. The derivative with respect to x dot just pulls out the a sub x. So this is going to be one of those terms. X, y, and z. I just want to show you how you expand that out. That then is d a sub x dx chain rule x dot plus d a sub y dot, I'm sorry, d a sub x dy y dot plus partial a sub x dz z dot. So in the process of applying the Euler-Lagrange operator, I'm going to call it, to this Lagrangian, which you best write out in all breadth, you generate lots of terms like this. And that's why it takes a little while to bring it into this form, because you've got v cross curl of a. Okay. However, one thing you can do is construct this thing, find its x component, you write this whole thing out, it's going to be pretty big, and then work your way to that result. Okay? Or you can meet in the middle, so to speak. So it won't be that bad. It's an important problem that the Euler-Lagrange equations for this Lagrangian give us the right expression, which we learned a long time ago. Good. So that's the gauge transformation and some Euler-Lagrange derivatives. Let's see how we're doing here. Okay. So next in this theme of what can we learn about a system without actually solving the equations of motion. Another interesting topic. This one concerns scaling arguments. It's called the Method of Similarity. And it makes use of the form of Lagrangian mechanics as well. So this one we're going to call the Method of Similarity. And first I'll start by just writing down the Euler-Lagrange equations. D R dot. So we're using Cartesian coordinates. And you notice both of these expressions involve a derivative. So we would be able to multiply the Lagrangian by some arbitrary constant, and it would leave the equation of motion unchanged. So because of this derivative form, if we multiply L by an arbitrary constant, or just write by a constant, the equations of motion remain or are left unchanged. Equations of motion are unchanged. Okay. So what good does that do us? In other words, I've got L or constant times L. It doesn't matter. If you do these derivatives, the constant cancels away, and I have the same equations of motion. Okay, so what good does that do us? Well, we're going to do a little construct here. So we're going to let L, since we're writing in Cartesian coordinates, we have a half. Putting the sum there, am I? Yeah. So system of many particles. So sum over 1/2 m r dot squared minus u of r1 to rn. R sub I equals 1 to n. So we're in Cartesian coordinates, standard Lagrangian, and we're going to specify something about this function where u is what's called a homogeneous function of the coordinates. So u is a homogeneous function of the coordinates. And what that means is u of, if you rescale the coordinates, so say instead of u of r1, I have u of alpha times r1, alpha times rn. Okay. Then what that does to the potential energy, it multiplies it by a factor k. Am I using k here? That's right. So it's alpha to the kth power times the original u of r1 to rn. That's a homogeneous function of the coordinates, and we could say of degree k. Okay. K is just a number, scalar number. I'll just leave that there. Okay. So if u is a homogeneous function of the coordinates, and now we're going to rescale coordinates in time. Oh, let's give an example first. Example. Newton potential. I'll do a few examples, but Newton potential U is equal to minus, I'll use the letter A divided by R. Okay. Then U of alpha R is equal to minus A over alpha R. Okay, I just substituted. Is equal to 1 over alpha times minus A over R, which is this 1 over alpha times U of R. Equals alpha to the minus 1 times U of R. So in this case, K is equal to minus 1. Here, K equals minus 1. So that's a homogeneous function of the coordinates of degree K. So, now let's rescale lengths and times. Now rescale lengths and times. Lengths times, so that the lengths go to, use an arrow here, lengths go to alpha R, and the times go to beta T. So, or we could say R prime is alpha R, T prime is beta T, and now let's construct our Lagrangian. That one up there, then this L prime is going to be sum over 1/2 m sub I, by the way. So the R sub I dot squared, that's a V, so that's a length over time. So we have alpha over beta squared R sub I dot squared. And then when we get to the potential energy, it's minus alpha to the k u of r. Okay, so the transformation we just talked about right there. So alpha to the k u of r. But since we rescaled lengths and time, we had alpha over beta squared because it's quadratic up there. So here's the thing. L prime equals L if this alpha over beta squared is equal to alpha to the k. Because if alpha over beta squared is equal to alpha to the k, then both of these expressions, both the kinetic and potential energy, are being multiplied by the same number. So there's a condition, and we're just going to solve that for beta. That means beta squared is equal to alpha to the 2 minus k. And now we'll plug in what our transformations mean, and we'll see what we have there. Okay. Or finally, beta equals alpha to the 1 minus k over 2. So this is actually a statement about physics now. Let's go ahead and translate it back. Okay, because this is the same as multiplying by the Lagrangian by a constant, which is leaving the equation of motion unchanged. Space here. So now we have, just translating this to here, we have t prime over t, that's our beta. And our alpha, we can say, is L prime over L, if I'm just talking about lengths. So, right, what the lengths up there are. So L prime over L to the 1 minus k over 2. And we're just talking about how the time scale versus how the length scale on our problem. So if we were solving the orbit, and we rescaled an orbit, say, of a planet around the sun, then it would still be the ellipse, it would just be a larger or smaller ellipse. That's the idea of rescaling. And finally, since we're just talking about times and lengths, we can say, or times and lengths generally scale as time proportional to length to the 1 minus k divided by 2, when all is said and done. Because which one is primed and which one is unprimed doesn't matter anymore. But if I get rid of the ratios there, I have to say it's proportional, right? There's a proportionality constant there. And this is the one we're going to work with. So we're just going to take our example and see what happens. We haven't solved the equations of motion, right? We've just found a relation between how time and length scales. So since we had that Newton potential to begin with, as my example, Newton, so we're talking about gravity, U is equal to A over R. Okay. What did we say? Alpha is equal to -1 for the scaling there. Therefore, T is proportional to L to the 1 minus -1/2. Negative times negative is positive, so 1 plus 1/2 equals L to the 3/2. So time scale halves. This is for the Newton potential. And if you square this, or t squared proportional to L cubed, and at this point you're realizing, well, that's Kepler's third law. Okay. Kepler's third law. In fact, we're going to do gravity again. We're going to do gravity in this semester. And we'll get to Kepler's third law with all the shenanigans, but here we just got it by pure thought. Okay, we didn't actually have to solve the problem. What we found is that the periods of orbits will scale as the length scale cubed, the square of the orbital times cube of the length scale. Yeah, so that is Kepler's third law. So I have two more examples, and I'll put those on the homework as well, because you can, you have this law now, and that'll be pretty interesting. Okay, so the two more examples that I want you guys to do, just, actually you leave enough space in your notes, because these aren't going to be a major problem. You leave the space in your notes as well, you can fill it in there. Example. Suppose your potential energy how do we want to do this? U of R equals, here's what we'll do. Alpha to the K. Let's do this. U alpha R equals alpha to the K U of R, where K is equal to positive 1, right? Plus 1. I forget the homework. I'm going to do these for you because they're actually done so fast. Let's just do them. Okay. So where K is equal to plus 1, let's go ahead and plug it in and see what we get. And then we'll kind of answer the question, what is this? So T is proportional to L to the 1 minus 1/2, K is equal to 1, is equal to L to the 1/2. Or T squared is proportional, other way around. What I want to write is, or L is proportional to T squared. I just changed the order, right? I square both sides, T and L. L is proportional to T squared. That would be a distance times squared law. Distance times squared law, put that in quotes, which of course we know as constant force or free fall. Example, free fall. And what is the potential energy for free fall? It's just U of, say, Z is equal to M times G times Z, right? And so, yeah, that's a length where it has the scaling exponent of K equals 1. So yeah, you get the distance times square law without actually solving the equations of motion. Now, the equations of motion are simple enough for that one. You can take it either way, right? But we did get it without actually solving them, distance times squared law. And the last example I'll do here is, suppose we have U of X is equal to A over 2X squared. That's a Hooke's law type of potential. I'm not using K because K has already been chosen. In fact, A is not such a good letter either. Let's use B. B over 2X squared. Okay, so now U of alpha X is equal to B over 2 alpha x, the quantity squared, equals alpha squared, and then when I pull that out, I've got b over 2x squared, so alpha squared u of x, and therefore k is equal to 2. This one's actually a really interesting result as well. So k is equal to 2, and we're going back into this expression right above here. So times and lengths, so t goes as L to the 1 minus 2 over 2, which is L to the 0th power. So times go as L to the 0th power, which means the times are independent of the length, okay? Times independent of lengths, exclamation point. So what is that? Well, this is Hooke's law, potential energy. The system is the harmonic oscillator, and the harmonic oscillator has periods that are independent of amplitude. So let's write that down. Harmonic oscillator, period independent of amplitude. And we can even write harmonic oscillator, L is a half mx dot squared minus u of x minus 1/2 b instead of k in this particular case, and t is equal to 2 pi over omega equals 2 pi root m over k, right? Okay. Right, so t is independent of the amplitude, and we have that right here with the scaling L to the 0th power. Okay, so yeah, these are actually really impressive results. They're very simple, but it's hard enough to solve equations of motion, so any piece of information you can get from your system by this type of analysis is well worth it. Okay, let's see how the time is today. All right. Now what I could do, I could add a nice little problem here, and I will. I use that part of the board. So let's call this a homework. It's a very basic application of what we just did here. So for a Lagrangian, L equals 1/2 mv squared minus u of r. So that's a single particle. Find the scaling behavior of mass and time. Okay. So instead of length and time, we'll do mass and time. And what you're going to do here is you're going to have to rescale the mass rescale the mass. I'm wondering if you do mass and time or mass and length. Yeah, mass and time. Okay. So you're going to do the same kind of rescaling argument that we did, except you're going to involve the mass, and you're going to get this kind of relation here that comes from both of these terms being multiplied by the same constant. Okay. And the example system that you can test your idea with right away is the harmonic oscillator, okay, which we just did for lengths and times. Harmonic oscillator. Okay, so in a sense it's up on the board, but go ahead and do it, and you'll see that the technique's pretty interesting. Okay, that takes us through that scaling discussion. We will see when we do small oscillations, systems of many degrees of freedom, that this argument holds there as well. Okay, so we did this for, we thought, a single particle. When we're talking about the harmonic oscillator, it actually goes for systems as well. Okay, let's see what we have on our plate next. So now we're going to move into actually solving mechanical problems. So far we generated the equations of motion, made some complicated Lagrangians already, constructed some of those, talked about what you can learn about a system from really general principles. Now we actually want to tackle the equations of motion. So we'll call this solving the equations of motion. In Lagrangian mechanics, and in mechanics in general. And here the terminology is reducing the solution to a quadrature, or to quadratures. So I'll just put that terminology here and we'll talk about what it means. Okay. And the best way to do that is to go back to Newtonian mechanics of 1 degree of freedom. Okay. So we're going to consider, and then we'll show what we mean in Lagrangian mechanics. So consider a system 1 degree of freedom. Actually, we're in the Lagrangian method right now, but the example I pull out will be one that we know from Newtonian mechanics. So this is 1 degree of freedom. Energy is conserved. Conserved energy. And L is equal to 1/2 m x dot squared minus u of x. That's not the most general one. We just had a more general one last time, but that's good enough. 1 degree of freedom, and we know that the equation of motion, we could differentiate that and get the equation of motion, but since we have energy is conserved, E is simply 1/2 m x dot squared plus u of x, and this is a differential equation first order. Okay, so how do we solve one of these in the most general sense? What we do is we isolate the dx over dt, so that's 2 over m times e minus u of x, take the square root. Okay, so that's dx over dt, that's velocity. And then we separate variables. So then we can say dt is equal to dx divided by 2 over m e minus u of x, square root. And then if we can do that integral, we could get t of x. So, or t is equal to go up to the next board so we can just showcase this thing. Right, so that's completely standard. So now what do we have? We have t equals the integral on the right side there. Integral dx, but now we'll call x prime as an integration variable, 2 over m e minus u of x prime square root x up here. And there's our answer. But what is this? This is t is equal to t of x. What we want is x of t, but we may not be able to invert this thing because it may not just have a special, it may not be a sine or a cosine or something. So this may be as far as we can get in a mechanics problem. And this is what we call the quadrature. Quadrature is a fancy old-fashioned word for integration. So, reduction of the problem to a quadrature. It's right here. So we reduce the problem, and this is often as far as you can get in closed form. That doesn't mean you're done yet, because you want that information x of t, and you may just have to work with this thing and analyze it. And you can get properties of the system this way, but then you have to dig into the integral. So that's the reduction of the problem to a quadrature. And in analytical mechanics, generally speaking, this counts as a solution, because this is as far as you can get analytically, and then you have to dig in there. Now, it doesn't mean that's as far as you can get in principle. For certain problems, we can keep going and invert this function, and in that case, then we have x of t. So this is what's meant by reduction to a quadrature. And so in Lagrangian mechanics, if we can reduce a problem to this level, then we're done, so to speak, and we're looking for classes of functions that can be reduced to a quadrature, because that's by no means a given. So, systems whose solution can be reduced to a quadrature. And I'm just going to give an example. And we'll make this example a homework problem. So suppose L is a function of, is a sum, here we go. L is L of Q1 to Qn, Q1 dot to Qn dot. And this one has a certain form. It is the sum of f sub I of q sub I dot squared minus the sum of u sub I of q sub I. So there's an example of a system that can be reduced to quadratures. You notice everything is actually decoupled here. So this one shouldn't be hard to recognize. So when I say f sub I of q sub I dot squared, I equals 1 to n, if it were x, y, and z, for instance, it would be, you know what, let's do an example here, because this one causes people some trouble sometimes. So the example for what I have here, but a simpler example, L equals 1/2 mx dot squared plus 1/2 my dot squared plus 1/2 mz dot squared minus 1/2 kx squared k sub x minus 1/2 k sub y squared minus 1/2 k sub z squared. Okay. That would be like 3 independent harmonic oscillators. Okay, completely independent. So you'd have this part going with this part. Okay, I've got colors here. This y going with this y and so forth. So that would be an example of this. This one's a little more complicated. But what happens is the Euler-Lagrange equations are completely decoupled. They don't have any mixed coordinates in there. So what you want to do is show that this type of system can be reduced to a quadrature, and you'll actually write out the quadrature for each individual component in this form. Okay. So as an example. Example, so example, prove for this Lagrangian reduced to a quadrature. Right there. So that's a good problem right there. It's slightly more general than this one because here we have just m and here we have some function of the coordinate itself. Now, one more point. If you do, say, d over dt, dl, dq dot minus partial L partial q equals 0, Euler-Lagrange equation, you may not choose the ith, the index I for that, because that's the index, the summation index. Go ahead and choose J or K or some other index, and you'll see immediately that you're just picking off the jth and the jth one right there. If you try to do it with I, you're going to make a mistake. Okay, so any operation you do now that's general in terms of the indices, you can't choose I, and that'll lead to trouble. And maybe I'll even give a hint for this problem. Hint, construct the energy. And when I say construct the energy, construct the sum over dl dq sub j dot q sub j dot minus L. And see what happens when you do that. That'd be an interesting one as well. But that or the Euler-Lagrange equations, just like I took the energy expression and got this thing right here. Okay. That could be a good place to almost, I think I'll add one more thing to the mix here. And that will be just a continuing discussion of this expression right here, just so you guys remember that. In fact, I'll make that a homework problem as well. All very basic. So this expression, the quadrature for u of x equals 1/2 kx squared. Okay. Because now we go into that expression up there. Now t is equal to integral x dx prime. We've got 2 over m e minus 1/2 k x prime squared square root. But E is 1/2 k a squared, right? Where a is, say, the amplitude. Because now we're talking about the harmonic oscillator. Harmonic oscillator, go ahead and write that out. So if we go in there, we would have x dx prime, and you see the 2 cancels there, so what we end up with is k over m a squared minus x prime squared square root. And I'm going to say, I'm going to draw an arrow there, and this is your homework. This turns into x of t equals a cos omega t plus some phase constant. So yeah, this is important. You're going to get an inverse cosine or an inverse sine out of here. Take your pick. By the way, there's a correction needed here. This was a plus minus, right? So we have plus minus here as well. And so yeah, the quadrature here with an integral that you can actually do, get your inverse cosine, you invert that, and then you actually end up with the complete solution of the mechanical problem. Right? A cosine omega t plus b. Okay, so yeah, this is the old concrete example you definitely want to be able to do before we just talk about these in the abstract. So here's one we can take all the way to completion. Good, so we have a couple of things to do here, and we'll leave it at that for now. Okay, see you guys next time.